LIGO and Virgo observatories have been telling us that they've been finding them, but just like anybody else, when I hear spooky sounds in the night, I get scared and I want to know what it's coming from. And so that's what I'm going to be talking about today. I'm going to be talking about electromagnetic counterparts, and what I mean by that is just flashes of light that are associated with these spooky sounds, gravitational waves. And that's the extent to which I will be dealing with gravitational waves in this talk. I'm just going to refer to them as spooky sounds and try and find out what's going on and look at them. Okay, and my tool for hunting for these, the light from these sounds, is a satellite observatory called SWIFT. And there's a question: why do I need a satellite observatory at all? Why can't I just use telescopes on the ground? So there's a few reasons. It's always night in space, so you can observe the whole day long. But there's also, if you see on this graph here, this is kind of cut off actually. This says opacity. And this is just showing you how opaque the atmosphere is to different wavelengths of light. And you see that there are large portions of the electromagnetic spectrum to which the atmosphere is essentially completely opaque. That means they don't come down to us. We can't see anything from them. Even if we were looking for it, we wouldn't see it. And that happens in gamma rays, X-rays, and ultraviolet, really high energy light. And then and these comes from all sorts of dynamics that I can't get into. But we need some stuff in space to detect that light. So, and because of that light's detected, blocked by the atmosphere, there's some things that we didn't find until relatively recently in human history. So can anybody just, I know there's some astro nerds in the house. Does anybody know what this is?
God.
Okay, this I know it looks like the Death Star, right? It's pretty cool. I'm sorry. This is the Vela satellite. It was launched by the U.S. military in 1967 to enforce the Atmospheric Test Ban Treaty. So the Soviets and the U.S. and a bunch of other people signed a treaty that they wouldn't test any nuclear weapons above ground, but the U.S. was suspicious that the Russians might be breaking this treaty, and so they launched this gamma ray detector, because there are gamma rays that are produced in these nuclear explosions, and they launched this gamma ray detector above Earth to see if anyone was breaking the treaty. And in fact, they were launched together like this, and then at very high orbit, and then they uncoupled from each other and went to opposite faces of the orbit so they could cover the Earth all at the same time. Very cool system. It never, ever detected nuclear weapons. However, in 1967, it detected gamma rays that weren't coming from the ground and instead were coming from deep in space. And because the military is all secret, they didn't actually tell any scientists about it for about 7 years. But once they did tell us about it, we spent that was 1967, we spent the next 40 or 50 years, I was not born then, to trying to figure out what these mysterious flashes of gamma rays are. And again, gamma rays are just really, really high energy light. And we found out that, in fact, that so much energy was being produced in these gamma ray bursts that they were the most energetic phenomena in our universe by far. This on the left you see is in powers of 10 scale. We have supernovas, which outshine our sun, according to this, by about 8 orders of magnitude, so they're about almost 1 billion times brighter than our sun. Gamma ray bursts are another trillion or so times brighter than that. And in the moment that a gamma ray burst goes off, they're giving out more energy and light than all of the other stars in the universe combined at that time. So these are really, really, really energetic big bangs. And because of all the stuff that we launched all these missions, including the Compton Gamma Ray Burst Observatory and other missions, trying to figure out what these were. And we figured out that there were these gamma ray bursts that I call long gamma ray bursts that are caused by the collapse of a star. So what's happening... Sorry, I'll pause it for a second. What's happening inside this star is the star is getting older, and a black hole has formed deep in its center. And the black hole starts to eat its way out of the center of the star, and in so doing, the matter is falling in on the black hole and creates these bright jets that point out of its poles. And these are made of gamma rays and other high energy radiation, and they shoot out of its poles. And this is the model that we built to explain what gamma ray bursts were, and it works pretty well. And it's just sort of like punching out of the star and eating up all of the matter from it, and then eventually it turns off, and you have a little afterglow thing. But in fact, this is not the end of the story for gamma ray bursts, because if you look at the population of gamma ray bursts, and this is data from the 1990s. If you look at the population of gamma ray bursts, you see this is in the number of seconds that the gamma ray burst lasts, and this is how many we found, and you see two distinct populations. There's longer bursts, and then there's shorter bursts, bursts shorter than 2 seconds, and that model that I was talking about before does not, and the model that I was talking about before does not work for these short gamma ray bursts. Nobody could figure out what they were, and in fact, they were so short that nobody could find that afterglow to figure out what it had been beforehand. We just saw these really bright bursts. We didn't know where they were coming from, and we were trying to figure it out. Similar to what I'm going to be talking about a little bit later with the gravitational waves, with the spooky sounds. And so we're trying to figure out what these gamma ray bursts are, and that's where SWIFT comes in. SWIFT is a 13-year-old mission. We're in low Earth orbit. We have what's called panchromatic coverage. That means we have 3 instruments on board that cover a lot of the wavelength. I'll talk about that later. It's the fastest slewing satellite in the sky. And what I mean by that is that unlike the other satellite observatories like Hubble and Chandra, SWIFT can repoint itself to point at a new spot in the sky an order of magnitude, 10 times faster than any other satellite observatory. And what this lets us do is it responds very quickly to these bursts. And SWIFT was launched this particular capability to figure out what are these short gamma ray bursts. What's going on with these short gamma ray bursts, because they would be able to get on target quick enough. And this is just a scale size representation. This is our original PI, Neil Gorell's, standing next to SWIFT before it was launched. It's about 17 feet tall. It's not big. It's about the size of my van. For comparison, Hubble is a big boy. It's the size of a school bus. But we punch outside of our weight and do some really cool science with it. We have, in order to do this science, to find these counterparts, these short gamma ray bursts, we have 3 instruments on board. We have 2 rather conventional telescopes, a UV and optical light telescope and an X-ray telescope. But we also have this, and those are really cool, and we can do a lot of real cool science with it, and the astronauts can read what I'm saying on the sky here. But this guy is really cool. It doesn't look like a telescope, but it is. It's called the Burst Alert Telescope. It's a really wide field of view imager, and it just sits there, and it can see up to 1/7 of the sky at any time. And it just sits there, and when a gamma ray burst goes off, it's able to detect the gamma ray burst, tell the spacecraft computer where that gamma ray burst is, and then the entire spacecraft turns to point its narrow field of view instruments at that spot to try and find the counterpart. Sounds familiar. And that's a really cool telescope, actually, because gamma rays are high energy photons, and they're actually so high energy that you can't focus them the way you would with a normal telescope, like with mirrors and lenses and that kind of stuff, because the photons will literally punch right through. They won't stop, they won't deflect, they won't bounce off, they'll punch right through. So you can't really do a conventional mirror. So what the Burst Alert Telescope does is it uses the dark arts. It studies gamma ray bursts using shadows. And I can't. So this is a depiction of the Burst Alert Telescope. Here we have what's called the coated aperture mask, which I'll just explain in a second. And then we have about a meter lower, we have the CCD detector. And basically what happens is, instead of focusing the light, what we do is we look at the shadows that are cast from the light hitting some of these filled-in pixels on the coated aperture mask and going through others. And from that we can figure out where the burst came from. And this is an example of what I'm talking about. You have the coated aperture mask. Some tiles are filled in with lead to lock the photons, and some are free. And it just punches it, and for the ones that it hits the lead, it doesn't go through, and otherwise it does, and it creates these shadows, and you can do very, very complicated data analysis that I don't understand because it's not my instrument. But you can do it and figure out, using these shadows, where these gamma ray bursts came from. And this is actually the coated aperture mask that is on board our spacecraft right now, being prepped for launch. Oh, it's kind of not great resolution, blown up this big, but you can kind of see what I'm saying. There's like 600,000 individual tiles. Some are half filled in and not, with a Gaussian, with a completely random distribution there. And using that, we figure out how to find gamma ray bursts. So this is what it looks like when SWIFT is in operations. We are orbiting the Earth in low Earth orbit, one orbit every 96 minutes. No. I'm sorry. We're orbiting the Earth once every 96 minutes, and we're performing other observations. We look at everything from comets to exoplanets to high energy astrophysical events. And SWIFT is just looking at anything that I tell it to look at, and it's just sitting there. And the Burst Alert Telescope is sitting there, and it's let's say In fact, right now I can figure out if I can do it in time. Oh no, I didn't do it in time. So we're looking at something in space, and then a gamma ray burst goes off, and the burst alert telescope detects it and slews to point at it and look at it really quickly. So that's essentially what it looks like when we discover something. Now, did anybody see any issues with that video? This is the astro nerds in the house. I'll start it again. Anybody detect any issues with this video? The animators at NASA are great, amazing. You'll see some of my animations later; they suck. But this isn't great, and because it makes it look like the spacecraft is going in what's called a retrograde orbit. It looks like the spacecraft is orbiting westward when the Earth orbits eastward. We are not. So that's it. That's not correct, but that's just my pedantry. Okay, so what happens when we detect a gamma ray burst with the burst alert telescope? I'm sorry, is that there's this image that's created by those shadowgrams I was talking about before, a bright spot, and then it sends that to the spacecraft computer. The spacecraft repoints its narrow field of view instruments, its X-ray telescope, and it creates another bright spot, which localizes it further. So we have this huge part of the sky, and we point something at it, and we find out exactly where it is. And then if there's a glow in the UV optical regime, then we can find it with that as well. And this is how we search for counterparts to short gamma ray bursts. Now, Swift has been up for 13 years now. This animation, I don't like this music. I don't know how this works. Okay, this animation was actually, thank you. This animation was actually produced in 2010 when we had just detected 500 bursts. But to this point, we've detected 1,150 bursts in our lifetime and localized about 93% of them. And this is the actual distribution of these bursts on the sky. And what you see is they're not concentrated. This is the Milky Way plane against the sky. And you see that they're not concentrated in the Milky Way plane, which means that they're coming from all over the universe. They're cosmological sources. They're coming from very, very, very far away. And Swift has found a lot of them and has let us do a lot of really cool science by following up. And in fact, to get back to it, remember, Swift was trying to figure out what are these short gamma ray bursts. And because of Swift, we were able to find the first ever counterpart, afterglow, to a short gamma ray burst. And using that data that Swift has produced in the past 13 years, the consensus was conceived that short gamma ray bursts are caused by the merger of two neutron stars. Now, neutron stars are just super duper 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 dense stars, and that have blown away all their other material. And Swift figured out from looking at these short gamma ray bursts and finding the locations of them, that when these stars get in orbit to each other and collide and explode, they produce these gamma ray bursts. And you see, again, these jets pointing out, gamma ray bursts, and then it fades very quickly. Exactly like what you'd expect for a short gamma ray burst. And Swift figured this out, along with the rest of the astrophysical community, but Swift was the first to find these counterparts. And so, to get back to these spooky sounds, so when we heard a few years ago these first sounds that they had heard from binary black holes, the LIGO people, the gravitational waves, the chirps that they were hearing, the spooky sounds, they told us that not only could they hear the chirps and the spooky sounds that were caused by black holes merging, but they'd also be able to detect the spooky sounds that were caused by merging neutron stars. And this is really exciting, because merging neutron stars produce short gamma ray bursts. And Swift finds short gamma ray bursts, so if we could find the short gamma ray burst that was associated with the merging neutron stars, we'd be able to find the light coming from the spooky sounds, coming from the gravitational waves. And that happened on August 17th, 2017. But before I do it, I'm going to say beforehand, they'd only detected black holes. I sort of talked about this. But the problem, again, with these spooky sounds is just like when you close your eyes and someone speaks, you can't really figure out exactly where they are. When you hear these spooky sounds, these gravitational waves from the cosmos, you can't really localize where they are either. You can sort of say, I think it's over here, but you can't really tell us where they are. So Swift is going to try and search for these gravitational waves. And so what happens is those regions of the sky that the people with the lasers at LIGO and Virgo gravitational wave observatories who hear the spooky sounds give to us and say, we think it's something over here, like over here, sometimes look like this. We call them banana regions because they look like bananas. And we figured out that because Swift can repoint itself so quickly, we can in fact do something that no other satellite observatory can do. And we can do something called tiling. And ground observatories do this, but this red circle is the size of the field of view of our narrow field instruments, the X-ray telescope and the UV optical telescope. They have a field of view. Remember I told you the Burstler telescope, the one with the shadowgrams, can look at 1/7 of the sky at all times, but our really fine instruments the size of their field of view is actually like something like 1/440,000th of the area of the sky. So if you want to look everywhere in this region to find the light that came from those gravitational waves that they told you over here, you have to tile. And so we figured out that because Swift can repoint so fast, Hubble and Chandra, they would go one and then have to wait several hours and then go to the other. We can retile in the order of minutes and seconds. And so we figured out that Swift is the only satellite observatory, only telescope in space that can do this, and we can do tiles, and in fact we can do a lot of tiles. But there's a problem with doing a lot of tiles, is that this is 1,800 tiles. If I'm doing one tile a minute, which is what we figured out would be the best way to do it, it's taking you 1,800 minutes to tile the whole thing, not counting the amount of time it actually takes to slew. And when you're going around the Earth, you can't actually observe it all the time, so this can take several days. So actually what they figured out was that what you can do is only tile the parts of this region that have galaxies in them. And so there are these galaxy surveys that people, Mike referenced them earlier, the galaxy surveys that people have produced. And what we do is we take this banana region and we figured out all of the galaxies that we already know are in that region. And then we only point the telescope at those galaxies because we know that merging neutron stars tend to happen in the outskirts of certain types of galaxies. And so doing that, we can chop down these 1,800 tiles to something more like 700, which is a lot, but we're able to do it. And so this is what happened on August 17th, 2017. I'll start that again. Oh, it didn't start again, but it's going to go over. So what you're going to see is that this gravitational wave is going to pass by. The two detectors in Livingston, Louisiana, and Hanford, Washington detect it. And then 1.7 seconds later, the animation timing isn't great, there's a bright burst. And what happened here is there was another spacecraft on August 17, 2017 called the Fermi Gamma Ray Burst Monitor. That's the name of the instrument on the spacecraft, but it's called Fermi, named after Enrico Fermi. And it detected one of these gamma ray bursts, this bright flashlight. It's kind of a bummer. Swift was trying to be the one to detect it, but Fermi detected it. But unfortunately, unlike Swift, Fermi can't repoint, and it can't localize them very well. In fact, Fermi can only tell us the same way that the LIGO folks do, that it just comes from some general region on the sky. This is what the signal looks like. This is a gravitational wave signal coming from two neutron stars merging together. Looks just like a ramping. Remember I was doing that. That's what it is. And then Fermi and also another spacecraft called Integral actually detected a burst in gamma rays and these really high energy photons that happened 1.7 seconds after. And remember, we were expecting a short gamma ray burst associated with this. So when this happened, all of the astronomers in the world jumped on it. I'm talking thousands of people, including us at Swift. And unlike the people on the ground, we didn't have the privilege, really, of having hours to prepare to wait till nightfall, because Swift can observe at all times. So we jumped on it right away, trying to figure it out and doing our tiling. And all of this was coordinated through an amazing network called the Gamma Ray Burst Coordinates Network, which is run by a colleague of ours, Scott Barthelme. And basically, it lets all of the satellites, observatories in space, talk to all of the telescopes on the ground and tell them that it's detected something. So when this gravitational wave went off and the gamma ray burst was associated, we knew immediately through this network. But there was a sort of a problem. So Fermi detected it, but remember I was telling you about the Gamma Ray Burst Monitor, the Burst Alert Telescope on board the Swift spacecraft. And I said it looks at 1/7 of the sky, and if it detects a gamma ray burst, we can find it really quickly because the spacecraft slews to where it saw the thing in the sky and looks at the afterglow to find the counterpart. But this is a problem. So this is a map of the sky. Everything in green, this is from the perspective of the Swift spacecraft. Everything in green is behind the Earth. This region right here is where the gravitational wave came from. So basically, Swift was at the wrong point in its orbit. Again, we orbit the Earth 15 times a day, going 17,500 miles an hour. Swift was in the wrong point of its orbit, and the gravitational waves and the associated short gamma ray burst came from the other side of the Earth. So we're kind of out of luck. But we could still do that tiling I was talking to you about, and so we did. And this is what the region that we were tiling looked like. This is a a map of the localization region that is where they think that it came from that we would have to tile. I can answer questions about why it looks that way in a little bit, but I'm just going to move on. This was again, this was an exceptionally exciting event. I don't know how. The most exciting thing that I've ever been involved with, and for people significantly older than me as well. No one had ever found a counterpart's gravitational waves. There was this, no one had ever detected gravitational waves, these spooky, spooky sounds from the merger of two neutron stars. And so we set out immediately to try and find it, and we actually did pretty well. We responded in 16 minutes, and what I mean by that is 16 minutes after we received the notice, the Swift spacecraft had begun observations to search for the counterpart, which is pretty good because it's in space. And we did 750 tiles to tile the region. We tiled 92% of the error region, which means that we looked at 92% of the places that they told us to look, and when the counterpart was eventually found, which I'll get to in a second, that made us more sure that the counterpart that was found was in fact the counterpart because we looked all the other places too and hadn't seen anything. And the counterpart that was eventually found is called AoT 2017 GFO. We observe it for quite a while. Let me show you, this is my animation, and you'll see it's not very good, but hopefully I can sort of explain to you what's going on. Okay, so again, this is a map of the sky. Everything behind the green and the blue is behind the Earth from the perspective of the spacecraft. The small red circle is the moon. The big red circle is the sun. Swift can't look at or point at or slew across the moon or the sun. This red line is a slew path of Swift. That means the Swift satellite observatory is pointing at this part of the sky, and then it shifted to point at this part in the sky. We do these all the time. We're very good at them. And these little dots here are the position of the spacecraft in Earth-centered coordinates, that if you're in the center there looking at the sky, where this position of the spacecraft would be on the sky. And this is our response to the merger event. So you see we're all doing all these really, really big loopy slews that we're very good at. No one else can do stuff like that. And then we start to jiggle around here. And this jiggling is we're searching the air region. This is actually what Swift did. And you see this, the spacecraft is streaking across the sky. This is every time the sun and moon go across, that's one orbit, 96 minutes. So it's about 2 seconds, 33,000 times faster than real time right here. So you see that this little dot is jiggling around, and what it's doing is it's trying to fill in that error region to search for the counterpart. And that's what we did. I think this is really cool. I don't, okay. Okay, so but what did we find? So Swift was not the first people to find the counterpart. As I told you, thousands of astronomers from all over the world were looking for it. A team from an observatory in Chile actually found the counterpart first, and it was a kilonova. And I'll get to what that is in a second. But this is the actual images that the UV optical telescope on board the Swift spacecraft took. Kilonova, what you see is that on August 18th, the day after the merger, there's a bright spot on the edge of this galaxy. It's called NGC 4993. And over the next several days, it fades. And Swift was actually the first people, even though we didn't find it, we were the people to discover the UV, the ultraviolet counterpart, because remember, the ultraviolet can't be detected from the ground. Later on, Hubble, which also has ultraviolet telescope, looked, but they couldn't get there fast enough to beat us. But hold on, what's going on? What's this kilonova thing? So I just want to sort of recap for a second. Remember, we were looking for these flashes of light that were associated with these spooky, spooky sounds that were caused by the binary neutron star merger, and it was found. And this is really important because never in the history of humankind had a astrophysical phenomena been detected both with gravitational waves, hearing it and feeling it, and with light. And this is very important because it brings us interesting information about the source that wouldn't be accessible otherwise. So remember how I told you that Swift built this consensus that short gamma ray bursts were caused by two neutron stars slamming together. Well, this was a consensus, but in fact, it hadn't been proved. What I mean by that is we were looking at these gamma ray bursts, these huge explosions, and trying to say, well, before this huge explosion, there were actually two neutron stars that were slamming together. But but you can't actually know that ever for sure, because just like, you throw an egg on the ground and now it's just eggshell and egg, you're trying to say it looked like an egg before, it's kind of a hard thing to do. But with gravitational waves, they can actually detect the neutron stars before they slam together, when they're still two separate objects, and then we can see the light, and we can take the short gamma ray burst, the light from it, and put it together with actual observations with gravitational waves, these spooky, spooky sounds of the neutron stars, and so we can see for the first time, 100% certainly, that short gamma ray bursts are caused by binary neutron stars. And obviously that's very important to Swift, because Swift is interested in short gamma ray bursts, so it's vindicating and very exciting from a lot of perspectives. This is a simulation that was produced by the NASA astrophysics people about what actually happened. So you have two neutron stars that are glowing, they're massive, they're shooting off gravitational waves, those waves going off, and they're inspiraling, and they're getting quicker and quicker and quicker and giving off gravitational waves, and eventually they merge, bam. And right now, you have these jets, just like I was showing you with the short gamma ray burst before. These are jets of gamma rays that were detected by the Fermi and Integral spacecraft. But in a second, you're going to see something very cool. You have these jets along the poles, but then you have material that is thrown off at the time of the actual merger. And this is what is called a kilonova. And so you have this kilonova, this cloud right here. And what's happening essentially is neutron stars, I didn't really tell you what they were, I'm sorry. Neutron stars are super dense stars that are essentially just made of neutrons, which is really strange, and it's a form of exotic matter that we don't really understand very well. But what's happening now is when these two stars slam together, their pieces, their neutron pieces, are thrown out. So you have the jets that are forming in the polar directions, but the material is thrown out and superheated and starts to combine. And you might have heard in the news that gold and platinum and other heavy elements were created, and this is where all the gold and platinum on Earth was created, and in fact 10,000 Earth masses of gold and platinum and other heavy elements were created in this blast. This is what's going on here. This really neutron-rich material is slamming into all the free neutrons that are thrown off by the merger of the two neutron stars, and it's able to form these really heavy elements that can't form in other situations. And so you get this kilonova, and then when the kilonova starts to cool, it changes color. And this is what astronomers, 4,500 astronomers from all over the world saw over the days, hours, days, and weeks after the event. And I can't stress, this is just the NASA logo. I can't stress enough how interesting that is. This is a little diagrammatic representation of what a kilonova is. You sort of see what I was talking about before. You have the jets coming off, and then you have the material that's thrown off from these two neutron stars when they merge, and it's neutron rich, and it gives off radiation that we can see, and we can see characteristics in the color of the radiation in the spectral lines that tell us that these elements are forming. But we can also know something really cool. So Swift, because we have what I was calling a panchromatic mission before, we have multiple instruments on board, we can actually look at the same object both with our UV optical telescope and our X-ray telescope at the same time. And we didn't detect any X-rays. And using the fact that we didn't detect any X-rays, we can actually determine that the kilonova, the short gamma ray burst, what its geometry with respect to the Earth is. So you can imagine the jets I was talking about before, you can imagine them pointed directly at you. And we can tell that because we didn't detect X-rays, they actually wasn't directly at us, and it was 30 degrees away, which is very important for detangling some of the physics that happens in these systems, that we can tell that its geometry helps us learn other things. I'm happy to answer questions about that. I think I'm running over time. I'm good. Okay, great. But there's still some, this is a huge win, but in terms of science, whenever you find something new, there's always questions that come up. So we had predicted that short gamma ray bursts were caused by two neutron stars slamming together, and that's true. The astrophysics community was right, it is true. But there are some weird things about this event that we don't really understand 100%. And that's what's really exciting about science, is that at every step, whenever you think you've got a handle on it, it presents new questions and new doors are open for you to figure out what's going on. So I hope that I sort of communicated how cool that was. I hope that I communicated to you the role that Swift played in this with its super fast slewing to search for these spooky, from the light associated with these spooky signals, and to quell the fears, the childhood fears of things that go bump in the night. Thank you.
Questions? just have a question. You're talking a lot about slews quickly. What's the mechanism for slewing?
Sure. Great question. So this is a 3D model. This is a.
Can you repeat the question?
Oh, I'm sorry. So the gentleman asked. I think it's. Project. Okay. So the gentleman asked. I was talking about slewing. That is rotating the spacecraft to point its telescopes at another spot really, really quickly, and he wants to know how are we able to do that. So this is a 3D model of the spacecraft from the back. I sort of flashed through some pictures earlier in the presentation. I'm sorry if it was too fast. The actual instrumentation, the telescopes, that's the Burstler telescope there on the other side. But what you see here are 6 wheels, 2 on each axis, and a set of 3. And these are what's called gyroscopic momentum wheels. They're reaction wheels. And the way that the spacecraft can repoint itself, if you might have done this experiment in a high school physics lab where you sit on a bar stool with a rotating chair, and then someone hands you a bicycle wheel that's spinning, and you move the bicycle wheel around, and you can actually get your whole body to start rotating in this way. And this is from a principle called the conservation of angular momentum. And what we do is we exploit this because in space you can't push off of anything. So when I want to turn, when I'm on the ground, I sort of, I push against the ground or I push against the wall. I can push against things to turn, Newton's third law. But in space you can't push against anything. There's nothing to push on. So we exploit this principle, the conservation of angular momentum, by spinning these wheels really quickly. And when we spin the wheels really quickly, the universe has to conserve angular momentum, so it makes the spacecraft spin the other way. That's how it works. Yes.
This is a great question to follow up with his, but, you look at the Kepler Space Telescope, which most of its reaction wheels have failed till now, and Swift has been in orbit for 13 years. What's the expected life expectancy for the Swift Space Telescope? Okay. And, going forward, the, LIGO and Virgo, and I think Japan's gravitational waves observatory tried to come online. You guys are at the end of your life expectancy, and
negatory. Sorry, I refuse to accept that. What I will say to you is that the only I apologize. The gentleman asked. He referenced a mission called Kepler, which is used to hunt for exoplanets. We have an exoplanet expert in the audience, maybe a few of them, so I won't embarrass myself by talking about them. But Kepler hunts for planets outside of our solar system, and it has a similar arrangement of reaction wheels, but most of them have broken. And because of this, it can't really do much science. And he's saying, how long does Swift have left? We're very old. Are we decrepit? Are we still going to be able to do science? So here's what I'll tell you, and it comes in a few parts. We have our space weather guys at NASA, and what they tell us is that the orbit of our satellite won't decay till the late 2030s.
Wow.
That's a long time. So what I'll tell you is that at this point, the only hard constraint on how long Swift keeps operating is if we keep getting funding from the United States government, which is up in the air always. But hey, we have gotten lucky that our momentum wheels haven't failed. I guess so you pull a bunch of momentum wheels off. Yes, I know. We got lucky when we pulled momentum wheels off the shelf when they were stocking the spacecraft. These, I think, are a slightly different model, but they're actually made by the same manufacturer who made the really crappy momentum wheels on the Kepler spacecraft. And we got lucky, and they're working fine. And our orbit's good to the late 2030s, and we have no consumables on board. So what that means is Swift doesn't use any thrust to move around. It just uses these gyroscopic momentum wheels, so it doesn't have to do anything, and we get all of our energy from the sun on these solar panels, so it's called no consumables. So as long as they keep giving us money, we'll keep doing science.
That's awesome. Thank you.
Yeah.
Thank you.
Yes.
So how fast can
That's a great question. So I've been telling you it slews really, really, really fast. I'm sorry. I got so excited about answering the question. So the gentleman asked, how fast does the spacecraft repoint? How fast does it slew? And how does that compare to the other big guys that I was telling you are really slow? So I've been telling you that Swift repoint slews really, really fast. But this is all in relative terms. It goes 1 degree per second on average. So if you break up the sky into 360 degrees, it takes 1 second to go 1 degree. That doesn't sound very fast, but there's some caveats. we go 1 degree a second, but we can point with exceptionally high accuracy, like to significantly less than the width of a human hair that you'd hold, out very far away from you. But also in space, it's hard to make these momentum maneuvers, these slewing maneuvers, because you have to spin the momentum wheels, and because you have to make sure not to break the spacecraft and to send it into a deadly cartwheel. You don't want to do that. So Hubble and the other people slew about 0.1 degrees per second. So about 1/10 of a degree per second. So even though 1 degree per second doesn't sound very fast, it is much faster than everybody else. Sure.
Since it's Halloween, what was the distance of this GRB compared to what a lethal hit distance would be?
Okay, so I say here 130 light years. What I mean by that is million light years. And that sounds like a really far distance. 130 million light years. A light year is about 6 trillion miles. But in fact, this... what? No, 6 trillion miles. Sorry, but you're wrong. So that sounds very far, but this was in fact the closest short gamma ray burst that's ever been detected. Now, how does that compare? So the gentleman asked, how does it compare to a gamma ray burst that if it was pointed right at us, it would sear the Earth and roast us like a marshmallow? Much farther. Was that the question?
Yeah.
Okay, much farther. Those would have to be in our galaxy. Our galaxy is 100,000 light years across. This is 130 million light years away. So it's much farther than it would have to be, even if it was pointed directly at us, even if it wasn't at those 30 degrees off axis that I was talking about before, the geometry of the system, it still wouldn't roast us. I'm pretty sure we're not going to get roasted, but you never know. Sure.
So, how many of Swift's short gamma ray bursts will LIGO detect, and how many of LIGO's merging neutron stars would Swift see if it were pointed in the right direction?
So this is a very good question. I'm going to be sure to repeat it. Jason asks, how many co-detections can we expect? So remember, I was telling you about the burst alert telescope and how it was pointed at the wrong spot in the sky to detect this short gamma ray burst at the time that it went off. But Jason says, when LIGO is running again, when the Gravitational Wave Observatory is running again, how often can we expect a co-detection? This depends a lot on your models of how often these happen and exactly what they look like. The latest models say maybe anywhere from 0.1 to 1 per year, which is not very much. Fermi is expected to detect anywhere from 1 to 7 per year. Sure.
So, it's not really a question, so I work also at Swift. I just wanted to point out this year, in February 6, 2017, our principal investigator, Billy Garrels, passed away. And he is the guy that was behind Swift, and he pushed a lot for us to be able to do this follow-up. And I think everyone in the team agrees that it's a pity that he's passed away, because he would have been so excited about this result, I cannot even explain. So I wanted just to mention him, because really, if we are doing this amazing science, most of it is just because Neil was there all the time with his enthusiasm, pushing everyone in the team.
So yeah, just to echo what Boris is saying, the principal investigator for our mission, the person who designed the mission, pushed for us to get launched and led us for the first 12 years, is over here on the left. His name was Neil Garrels. He died last year. He was an amazing astrophysicist who really pushed Swift to continue to be crucial to this effort of finding counterparts, and our science paper is actually dedicated in his honor. If there's no more questions, thanks you guys for being great audience. Okay, you have a question.
So one more question. Our camera wasn't quite recording at the beginning. Can we get another audio representation of the gravitational wave?
Wait.
Let's make sure that you have 56 seconds.
Okay, so this is my best representation of a compact binary merger. Please do it for your children and friends at home. Spread the love and the spooky sounds around.
All right, so